So we are going to move to another presentation about spatial indexing in GeoParquet format from Eugene Cheipesh from Azavea. I have no idea if I pronounce your name correctly. Eugene? Okay, not too bad. You're very kind.
All right, let's try to keep this lightning. So this is a talk on spatial indexing in GeoParquet. Big disclaimer is that this is very much a discussion in progress. Hopefully this will be a nice on-ramp. If I say something that is untrue or I miss something, it's probably because I don't know better. So that's the issue number. Yeah, okay, so let's recenter ourselves. The problem we have is that we have this nice cloud native data format. We want to store vectors in it. This is very much like write once, query often type situation. The reason shapefiles aren't good enough is because you can have hundreds of gigabytes of data. And really, the focus here is to make something that's portable across languages, ecosystems, so kind of like the least weird. And the implication is if we're going to be publishing hundreds of gigabytes of data, it probably would be good to be able to efficiently select it spatially. And that just means by bounding box of geometry. In practice, this always ends up being a filter in two steps. The first filter is just a filter by bounding box that discards a majority of your data set. And then there is a refinement after the geometries have been read in memory to do the actual geometric intersect, use spatial predicates, fancy stuff, expensive. So in order to support that, we kind of have to have a couple of components in place, right? We have to have our data in chunk format so we can discard large parts of it. The data that's spatially located has to be written together. That's kind of not what I'm talking about here, but it's a major assumption that this has happened. So it would be legitimate to discard large chunk of your data set. And there has to be a spatial metadata that we can use to discard chunks without looking at them correctly. So our model is super simple. We are storing features in a table. There's a geometry and attributes, simple features if you like. GeoParquet supports storing more than one geometry column, but for purposes of this discussion, we don't care because we can only index on a single geometry. So let's just go with this model. So yeah, a lot of what we need is already just in the Parquet format themselves. So this is slightly simplified version of the Parquet layout on disk. And let's just talk through it for a minute. So we have chunking on 2 dimensions. Rows are chunked in row groups. That's the purple box. And these things are, we assume, are going to be spatially collocated. And then the attributes are chunked by columns. This is what we mean when we say that this is a columnar format. So all the geometries are written together, then all the GUIDs and names that you don't see, and so forth and so on. And at the bottom of the file, we have a footer. This is actually how we route when reading the file to the part that we need. We have the schema, we have a place to shove extra KeyValue metadata, and we actually have the offsets, right? So that's nice. We're focusing here on WKB, well-known binary, because this is the most portable format. And I guess like this is one file, but one file will typically be between 32 to 128 megabytes. So actually there could be, a dozen or hundreds of these things somewhere. So GeoParquet, how did we make this geo? The same way that we did with the GeoTIFF. We just added some geo metadata that qualifies the geometry. We know what projection it is. We know what kind of encoding it's using, whether it's planar sphere or planar or spherical geometry. And we can actually put the bounding box right there in the metadata. Is that our way to spatially filter this? Well, unfortunately not, because that's just nowhere near selective enough. Even like a 32 megabyte file, which would be a single Parquet file, can have tens of thousands of geometries, depending upon how big it is. I made that number up, but the point is that in order to read them, decode them, and do the intersection is still prohibitively expensive, experiment shows. So we have a couple of options to actually implement a spatial index. One is using space filling curves. This is like very popular. This is what GeoMesa, GeoWave, lots of databases do. Space filling curves are things like Hilbert, Z2, S2, lots of others, I guess even H3. I'm going to argue that this is kind of inappropriate for use cases, because what you do here is you intersect your geometries with some kind of recursive grid, and you use the IDs of the grid to do your indexing. So the point is that unless you're storing points, you're inevitably going to end up in the situation where your geometry is associated with two cells that often ends up being data duplication. And the math of actually trying to use this indices is like super weird and does not requires its own support libraries. So this flies in the face of keep it simple requirement. So I'm going to say we don't want this. It's wildly inappropriate. Second option that we have is let's use the KeyValue metadata that we have per column chunk, kind of like the row division of our data. This would work, but this would require us actually changing the way that the filtering happens, actually changing all the Parquet clients. That's a lot of work across a lot of projects, probably not a great first start. So now we're down to either adding a column, basically now we're down to adding a column or using some sort of native geometry format. So adding a column that simplifies the geometry in a way that Parquet can understand, in a way that Parquet filters are able to understand is what we're talking about here. So in our mental model, we just say, great, there's the geometry, it's complex, it's bytes. We cannot express any kind of predicate on it using the existing Parquet libraries. But if we express a bounding box as an X in the Y column, these are primitive values and we can filter on these. And the story actually gets much better with this approach because the Parquet format already has the support for storing stats for the minimum and the maximum value for primitive columns in the footer. This is the part that is read first. So your predicates are now being evaluated before the column chunks are being read, and that's filtering, right? That's kind of like your actual mechanism. It actually gets a little bit better. As of 1.1, it also stores stats for pages. So there's kind of two levels of filtering. That seems good. Yeah, I guess you only have to do this once during write. It's like a little bit unfortunate that you're introducing data into the data set, but what you get is quite powerful. And this works, and we'll talk about that in a second. But the really neat thing about it is this data structure maps very neatly onto an idea of an R tree. So in the data layout, the column chunks are composed of pages, files are composed of column chunks, and of course, spatially, the bounding box of a column chunk is the bounding box of a page, and the bounding box of a file is the bounding box of all of the column chunks.
Eugene, we are coming to the end of the time, so if you could.
Oh, okay. Yeah. Great. So this works. Actually, Grigory Pomachan implemented this and ran with this in Carto Spatial Extensions, testing this on 10 million polygons versus reading this on the CSV that ran for 60 minutes. The same kind of full scan for Parquet runs for 4 minutes. And using this bounding box filter with the push down predicates takes the query down to 1.5 seconds. I'll say one thing is that you can do this. This isn't great for points, and perhaps you can do even better if there was a Parquet native way of encoding geometries, which is already being discussed in GeoArrow and kind of requires on splitting the X and the Y column in order to be able to do the same filter on X and the Y. So I guess with that, I will stop.
Thank you so much for your presentation, Eugene. And